Hi everyone, I'm Marwa, and today I'm going to tell you about our work on resilient alerting protocols for blockchains. This is joint work with Lorenz from Chainlink Labs, Ittay, my PhD advisor from the Technion, and Ari from Chainlink Labs and Cornell-Tech. So smart contracts rely on timely alerts to get information about off-chain events. Now, the problem is that alerters can be bribed to stay silent and block the information from reaching the blockchain. So in this talk, we formalize this problem as a game between a bribing adversary and the alerters. We prove that for any alerting protocol, the amount that a briber needs to pay in order to silence all alerters is at most quadratic in the number of nodes. And finally, we design alerting protocols that asymptotically achieve this upper bound and discuss their trade-offs. So let's start with some very quick background. We have our blockchain. We have some pieces of code running on the blockchain. Those are the smart contracts. And users or nodes can interact with the blockchain by sending transactions. Now, the thing is, the blockchain cannot access information outside of the blockchain in the real world. And the solution that people have been using to this problem is what we call oracle networks, which are just a set of servers or nodes, as we call them, that get the information from the real world, aggregate it based on some protocol, and send it to the smart contract. And those nodes get paid to do their job. And to explain what can go wrong here, let me give you an example. So for our example, we have a company that wants to implement a flight insurance policy on the blockchain. So you have a smart contract that says, well, if your flight gets canceled, then you get $1,000. So users can go and buy this insurance policy by sending a transaction to the blockchain. And now, unfortunately, your flight got canceled. The smart contract doesn't know about this, but we have our oracle network, which gets this information and sends it to the blockchain. And we call this, this transaction that sends the information to the blockchain an alert. Okay, so we're alerting that some event happened. And once the smart contract hears about this event, it pays the users their insurance money. Now, let's say that an adversary, the insurance company, does not really want to pay all those users $1,000 each. So what they can do instead is they can go to each of the nodes in the oracle network and offer a bribe. So say, I'm going to pay you some amount. In exchange, you just don't send this information to the smart contract. And if this amount of money is high enough, the oracle network will block the information from the blockchain, meaning that the users will not get their money back, and the insurance company gained some amount of money that it would otherwise had to pay to the users. In this example, the adversary and the contract operator are the same, but it doesn't have to be this way. And we don't want these types of things to happen. And in order to solve this problem, we first have to model it. And in our world, we assume that the network is synchronous, meaning that the message propagation time is bounded. Okay, so first we have our smart contract, and our contract operator, the person who wrote the contract, funds the smart contract with C tokens, and those tokens will be used as a reward to the oracle nodes for good behavior, for participating in the protocol. Now, in our oracle, we have n nodes, and we assume they all are rational, meaning that they aim to maximize their utility. Or in our case, they aim to maximize the amount of tokens they have. So to participate in the protocol, each node has to lock lambda tokens as stake with the smart contract. And the smart contract can slash these tokens to penalize the nodes for misbehavior. So if the node is caught deviating from the protocol, the smart contract can penalize it by taking away the lambda tokens. And the protocols that we care about is what we call C-lambda alerting protocols. So an alerting protocol is a protocol that incentivizes nodes to actually send the information to the blockchain. And the C-lambda alerting protocols are alerting protocols where the operator funds the contract with a constant value C. and each deviating node gets slashed by a penalty of lambda. Now, this was our setup, and let's say that some off-chain event happened. And ideally, we want the smart contract to hear about it. Either all nodes or some of the nodes have to send this information. And here, and throughout the talk, we assume that nodes and basically anyone can check whether an alert is needed. Okay? Now, the question of how to do so is a different one, and we don't deal with that here. But right before the nodes can actually send their alerts, we have our adversary, who is also rational, and may gain G tokens if the information is blocked from the smart contract. So the adversary offers each node a bribe in exchange for the node not sending the alert. And now each node has two options. It either takes the bribe and risks losing a penalty of lambda if it's caught deviating, or just follows the protocol, whatever that is, and gets some reward based on the specific protocol. And of course, we want to make it as hard as possible for the adversary to bribe all nodes. So we define this measure of sigma bribery resistance, and we say that a protocol is sigma bribery resistant if for any adversary's budget that's below sigma, we know for sure that an alert will be published. And our goal is to have protocols with the maximum bribery resistance possible. Now, this is the world that we operate in, and let's see a very simple example of an alerting protocol. So in our protocol, we have our N nodes. We have done the setup stage, and let's say that an event happened. Now, all nodes can alert. All those that did alert equally share the operator's cost. So if, in our example, k nodes did alert, each one gets C divided by k tokens as a reward for their good behavior. And all the nodes that did not alert, they get penalized by having their lambda tokens burned. But in exchange, they get the bribe that was offered to them. And of course, if none of the nodes alert, then the smart contract will not know that something went wrong, so no one will be penalized. Now, in this simple protocol, let's look at one node, for example, node 3 in our protocol, and let's say that node 3 decided to alert. Now, the best case scenario for node 3 is if it's the only alerter, because then it doesn't have to share the reward with anyone else. It gets the entire operator reward. But if the adversary goes to node 3 and offers it a bribe that's higher than C, the maximum reward, plus lambda, the penalty that it might lose for deviating. In that case, it is obvious that it's better, node 3 is better off not alerting and taking the bribe. And this is true for any node, actually. So if the adversary is willing to pay n times lambda plus C tokens, or an amount that's linear in the number of nodes, then she can block the information from the blockchain. Okay? So this is the maximum that this protocol can handle, but we want to do better. And to do better, the idea would be to use the burnt penalty. Instead of burning these lambda tokens each time, we will use these tokens towards the reward pool. So now, these slash tokens will be used to reward nodes for good behavior. And in fact, the idea of using penalties as rewards is not new. I couldn't find who the first to use it, but I know that Uma's optimistic oracle used it at some point. But now what we have is the maximum amount of reward that any protocol can offer is C plus lambda n, or actually is bounded by C plus lambda n. So again, let's take one of the nodes. If the adversary offers this node a bribe of C plus lambda n, or anything higher, then this node is better off taking the bribe and not alerting. And this is true, again, for all of the nodes. So now, if the adversary is willing to invest n times C plus lambda n, or an amount that's quadratic in the number of nodes, then she for sure can block all alerts from reaching the blockchain. And here we did not assume anything about the protocol itself. In fact, this is true for any C lambda protocol. So the maximum bribery resistance that we can achieve in any C lambda alerting protocol is quadratic in the number of nodes. Now, on the one hand, this doesn't sound so good because we have an upper bound on the resistance that our protocols can achieve. But in practice, we are investing an amount that's linear in the number of nodes. So we have n nodes working. And in exchange, we get a cryptoeconomic security that's quadratic in the number of nodes. So the next step would be to answer the question, can we actually achieve this quadratic bound? And this is what we're going to see in the rest of this talk. So what's going to happen now is we're going to define two game theoretical constructions, the simultaneous game and the sequential game. We're going to show that for each of the games, we get the quadratic bribery resistance that we want. And then for each of the games, we will see how to actually implement it. So a protocol or protocols that implement those games. All right. Let's start with the simultaneous alerting game. And this game has two stages. In the first step, it's the adversary's turn. And the adversary offers each node a private bribe. Okay? The bribes are private. And in the next step, all nodes need to decide whether to alert or not. Now, the second step happens simultaneously, meaning that no node knows what others are doing before choosing its own action. And yet we assume that nodes do not collude here. After the alerting part was done, the smart contract can then penalize and reward nodes based on what it needs to do. And so if at least one node alerts, all non-alerters lose a penalty of lambda, and all alerters get an equal share of the slashed value. And from now on, I'm going to ignore the constant operator cost because we show it doesn't affect our results. All right, so this is the game construction, and let's see what properties does it offer. So we analyze the game, and let's see at what one single node can get. So if a single node gets a bribe that's below lambda, then the dominant strategy for this node is to always alert, meaning that regardless of what other nodes decide to do, this node is always better off alerting because the bribe is too low, basically. And the other end of the spectrum is also true. So if the bribe offered to a node is higher than lambda n-1, then not alerting is the dominant strategy because the bribe is so high that it just makes sense not to alert. And the question is, what happens in this range in between? And to answer that, we're going to have to look at what the adversary makes out of these attacks. So this scale shows what is the adversary's gain from the attack. And of course, if the adversary's gain is below lambda n, then at least one node will get a bribe of under lambda, which means that this node will alert, as we saw in the previous slide. So in that range, we're good. At least one alert will be, we will have at least one alert. And if the adversary's gain is higher than lambda n times n-1, then the adversary can offer all nodes enough bribe so that none of them will alert. And for the range in between, it turns out that there's no symmetric pure strategy Nash equilibrium, meaning that the state where all nodes choose to alert or all nodes choose not to alert is not stable. And any node can switch its choice, and this will result in a higher gain for this node. What this means for the nodes is that they do not know what the best thing to do for them is, whether to alert or not. So the next best thing to do would be to choose with some probability whether to alert or not. And when we're talking about probabilistic choices, we're talking about mixed strategy Nash equilibrium. And in fact, we can show that in this range, if the adversary offers a bribe to the nodes, the expected utility of the adversary is always non-positive, meaning that the adversary is always better off not offering any bribe. So for this game, the threshold for a successful attack is only if the adversary's gain is higher than lambda n times n-1, which is quadratic in the number of nodes. So what we showed is that this game actually reaches this upper bound that we showed earlier. And the question is, well, how can we implement it? And to implement it, we start with a very strong network assumption, which is that the time it takes to write a transaction to the blockchain is constant and known in advance. Now, yes, this is a very strong assumption, but bear with me. If we are OK with this assumption, the protocol becomes very simple. We give all the nodes one time slot to alert. All those that think an alert is needed have to send it in that time. Then we wait for delta write time steps. And right after the delta write time steps end, the smart contract decides who should be penalized or rewarded, if any. Now, this is a protocol with some very nice properties because it runs in constant time, right? We have to just wait for this constant amount of time. But if an alert is needed, then we need a linear space on the blockchain to store all the alerts. And it achieves the quadratic bribery resistance that we wanted so bad. The only problem is that networks do not really work like this. But in fact, the key point of this that we used from this assumption is that participants act before seeing each other's actions. And whenever I say that, the first thing that comes to mind is, well, why not use a commit reveal scheme? And the idea would be as follows. We have our alerting period, and we divide it into two. So we have the commit phase, in which all nodes should commit to their choice to whether to alert or not. And then afterwards, we have the reveal phase where nodes should reveal their choices. The only problem with this type of scheme is that nodes can still reveal their choice early, and in fact, they can prove to the adversary that they chose a certain action. And if they do that, they actually break simultaneity, and this causes the attack cost to drop to n log n instead of n squared, which we don't want. So to still achieve this simultaneity, we still use a commit reveal scheme, but with a twist. We actually use a TEE-based commit reveal scheme. So here, we relax the strict network assumption, but we do assume that nodes have access to TEEs. And again, we have the commit and reveal phases. Now, each node uses their TEE to commit to a choice and send this commitment to the blockchain. Then, in the reveal phase, to reveal, the TEE will allow the node to reveal its choice only if the node proves to the TEE that enough time has passed. And to do that, we use the primitive of proof of publication from this very nice paper called Ittay. And again, this protocol runs in constant time because we just have to wait for the 2 periods to elapse. We do require linear space on the blockchain, but again, we have the quadratic bribery resistance that we wanted. So this was the simultaneous games implementation. And we worked really, really hard to achieve this simultaneity property that the game required. But what if we're OK with having a bit less of bribery resistance, still quadratic, but in exchange, we lose this simultaneity assumption. So what we're going to do next is I'm going to show you the second game, the sequential alerting game. And the idea here appeared in Chainlink's 2.0 white paper. So the game goes as follows. Before the protocol begins, we sequence all the nodes. So each node gets an index. And each node is allowed to alert only during its time slot based on the sequence. Now, if node I alerts, then the alerting round ends, meaning that all nodes with a higher index cannot alert. And previous nodes that chose not to alert pay some penalty of lambda, pay the penalty lambda. And node I gets all the slashed penalties. So it gets lambda times I minus 1 as a reward. And now, to analyze this game, to see what the properties that we get is, it turns out that if the adversary's gain is below, anywhere below lambda n times n minus 1 divided by 2, then there exists a node that will alert. And to do that, we analyze the subgame perfect Nash equilibrium using backward induction. I'm not going to go into the details. But if the adversary's gain is anywhere higher than this value, then she can bribe all nodes into silence. So the threshold for attack success for this game is if G is larger than lambda n times n minus 1 divided by 2, which is, again, quadratic in the number of nodes, but half of what we got in the previous game. Now, unlike the other game, implementing this one does not require any additional assumptions, right? Just the regular synchronous network is enough. And actually, the description that I gave you is already the way to implement it. So what this protocol gives us is it works in linear time because we have to wait for all the slots to pass. But in exchange, we get constant space on the blockchain because we either get 0 alerts, which is OK, or we get at most 1 alert. And again, we reach the quadratic bribery resistance that we aimed for. So to conclude, we formalized this game of bribery between the bribing adversary and the set of alerters. We saw that the maximum bribery resistance that we can achieve is quadratic in the number of nodes. And we showed 3 different protocols that achieve this quadratic bribery resistance, each with a different set of assumptions and their trade-offs. So that would be it. Thank you very much.
Thank you so much.
Hey, thank you. I'm curious about the model. I thought most oracles have some fault tolerance built into them. So a single node operator couldn't, say, influence the smart contract entirely on its own, but rather they would need to come to some consensus before sending over the real world event. So how would that impact this analysis?
So what you're mentioning has to do with the way we decide whether an alert is needed or not, which is not exactly the problem that we're trying to solve. The problem that we are trying to solve is, let's say that someone wants to block this information altogether from reaching the blockchain, right? So if we have this consensus protocol that is running, let's say, that the Oracle network is using, but if the briber can bribe all the nodes not to participate in the consensus protocol, then there will be no result for the consensus protocol, right? The liveness of the protocol will be affected. And that's what we're trying to avoid here.
Okay, thanks.
One question I have is, when we observe oracles in the wild, right, if you had to have sufficient amount of gains from a single incidence of bribery for it to be worthwhile.
Right.
Well, these oracles, of course, if it makes a mistake once and it kind of loses the community's trust. So how do you think about the sequential nature of trusting the oracle and how that reputation degrades very quickly? You know, the example could be like Polymarket and their oracle. People very quickly figured out that oracle is not as good, and now they're in the process of replacing it.
I'm so sorry, I'm not sure I got the question. Can you?
Yeah, so I guess in your initial motivation, it's the malicious actor has to bribe with sufficient amount in a single round, right? But in many incidences, it actually takes multiple rounds for the oracle to develop a reputation. And I was just wondering if you thought about the bribery sequential nature of it and whether the bribery needs to be high enough on a single case or it could be over a period of time.
So what we deal with here is a single instance of running the protocol. We did not look into multiple ones, but we can treat them as just multiple instances of running the same protocol. And to participate, you have to still lock stake for every one of these instances.